The following is presented by the Computer History Archives Project.
The electronic digital computer, completed in 1946, was named the ENIAC, an abbreviation of Electronic Numerical Integrator and Computer. It contained about 1,500 electromechanical relays and 18,000 vacuum tubes. In the newest models of many computers, there are no electromechanical relays and not a single vacuum tube. These computers make use of so-called solid-state electronic components, semiconductor diodes and transistors. They provide for electron flow through solid substances rather than through vacuum or gases. Semiconductor diodes are made of metallic crystals, usually of germanium or silicon. They conduct current in one direction only. Transistors are also crystalline devices. They control current flow by a principle that resembles that of the triode vacuum tube. These devices offer many advantages over vacuum tubes and relays in size, reliability, ruggedness, power consumption, and operating temperatures. It is the purpose of this film to see how various logic element circuits operate to control the flow and processing of binary data. Let us consider diode circuits that function as AND and OR gates. You recall from a previous film that the logic AND gate has two or more inputs and a single output, and that when all inputs are binary ones, the output is 1. 1 and 1, output 1. Conversely, when any or all inputs are 0, output is 0. A positive voltage pulse can represent a binary 1, and a no pulse 0. If desirable, a negative pulse may be used for the 1, with no pulse as 0. The designation must of course be used throughout the system. 1 and 0 can be simply high and low, as long as the voltage difference is great enough for them to be considered opposites. The AND circuit is made up of two or more diodes and a resistor. The cathodes receive the circuit inputs. The anodes, counterparts of the plates in vacuum tubes, are connected to the resistor, which is returned to a relatively high voltage, say plus 100 volts. Plus 10 volts may be the high input voltage, binary 1, and 0 volts, the low, binary 0. When both inputs are high, both diodes conduct, offering very little impedance to the electron flow. There is therefore almost no voltage drop across them. Most of it is across the resistor, making the voltage at the output point plus 10, high. Thus the circuit meets the 1 and 1 inputs with a 1 output requirement for an AND gate. When both inputs are low, both diodes again conduct, and with almost no voltage across them, the output voltage will be low. This satisfies the 0 and 0 for a 0 output requirement. Now let's see what happens when one input, either one, is high and the other low. The low input diode will conduct and drop the output point to the low voltage. This voltage on the anode of the high input diode will make it more negative than the cathode, and therefore cause it to cut off. It therefore cannot raise the output voltage above low. Thus it remains low. The requirement, 0 and 1 inputs with a 0 output, is thus satisfied. This type of circuit, with positive bias on the diode anodes, is known as a positive logic AND gate. The function of the OR gate is to act as a mixer or buffer. When there is a binary 1 on at least one of the inputs, the gate permits a binary 1 output. 0 inputs mean a 0 output. The OR circuit, like that of the AND gate, is composed of 2 or more diodes and a resistor. Here, however, the cathodes are connected to the resistor, and it is returned to a negative voltage, say minus 100 volts. This circuit is the exact opposite of the AND gate. The inputs, as before, may be plus 10 volts and 0 volts, as high and low. When both inputs are high, both diodes conduct, and the voltage drop at the output point is high. With binary 1s, then, as inputs, the output is 1, correct OR gate performance. When both inputs are low, both diodes again conduct, resulting in the low output. Binary zeros in, binary 0 out, again correct. When one input is high, it conducts, and output is high. This voltage is on the cathode of the other diode, which has a low input. Its anode, with low voltage on it, is more negative than the cathode, and therefore cuts off the flow. This condition is satisfactory for an OR gate circuit, the rule being that with a binary 1 at any input, the output is 1. 1 or 1 input gives a 1 output. Let us now see how transistor circuits function as logic elements. First, taking a general look at the key component, the transistor. It consists of 3 elements: an emitter, a base, and a collector. They are somewhat equivalent to the 3 elements of a triode vacuum tube. At the interfaces, which are known as junctions, there is diode-type action that can be used to switch currents off and on. Symbolically, a transistor is shown this way. This one is commonly used in computers and is known as a PNP transistor, positive, negative, positive. It requires a negative collector bias voltage. The emitter is grounded to 0 potential. When a negative voltage is applied to the base, the resistance of the transistor becomes extremely low. Consequently, there is current flow through the transistor. The effect then is that of a closed switch. When 0 or positive voltage is applied to the base, the resistance is extremely high and current flow virtually stops. The switch is open. Switching in this manner is the commonest use of transistors in computer logic circuitry. A transistor in this configuration, known as common emitter, is used as an inverter or NOT circuit. It changes a 1 or high to a 0 or low, and vice versa. It may be transistorized in this way with the use of 3 resistors. The collector resistor is negatively biased. The base resistor positively biased, and the emitter grounded to 0 volts. The value of the base bias is such that when the input is low, that is 0 or positive voltage, the base bias remains positive. Collector current does not flow, and output voltage becomes negative, high. Thus, a 0 input becomes a 1 output. When the input is high, the negative voltage reverses the bias on the base, making it slightly negative. Base and collector currents then flow, and output drops to 0 volts, which is low. Thus, a 1 input becomes a 0 output. The inverting function appears in other transistorized logic circuits. This is a typical transistorized logic gate. Its operation is similar to that of a diode AND circuit. The resistor is returned to a relatively high negative voltage. The base leads are the inputs. Output is taken at the collector. Again, binary 1 is a negative voltage, and binary 0 a 0 or positive voltage. The transistors are turned on by applying a negative voltage or binary 1 to the bases. Current will flow when and only when both inputs are negative, that is, binary 1s. The transistors then act as closed series switches. This satisfies the requirement for an AND gate. Both inputs 1 to enable current to flow. In this case, the output voltage is 0, which represents binary 0. Conversely, when current does not flow, output voltage is negative, representing binary 1. Thus the circuit, though acting like an AND gate, inverts the output. For this reason, the circuit is referred to as a not AND or NAND gate circuit. If the inputs are not both binary 1, current cannot flow, so the output is binary 1. This is in keeping with our definition of a NAND gate circuit. This circuit operates in a manner similar to that of a diode OR gate, but is known as a NOR gate because of transistor inversion. The transistors are in parallel with each other and in series with the collector resistor. Parallel switches are a good analogy. If one of the transistors is turned on by applying a negative voltage, binary 1, to the base, current flows in the transistor, and it acts as a closed switch. A 0 output results because of the inverting action. If instead the other transistor is turned on, the same type of action occurs, hence the OR gate similarity. If both inputs are 1s, current flows in both transistors, and output is binary 0. If both inputs are 0s, current does not flow, and output is binary 1. Symbolically, the NOR gate may be represented as an OR gate with an inverter. This type of gate may be implemented by using a single transistor and appropriate resistors with 2 or more inputs to the base. The values of the resistors determine the circuit's responses to inputs. When both inputs are binary 1s, negative voltages in this case, base and collector currents flow, and output drops to 0 volts. Thus, 1 inputs gives a 0 output. If one input is 1 and the other 0, collector current will still flow, resulting again in 0 output. Thus, 1 and 0 inputs give a 0 output. If both inputs are 0, the base is positively biased. Collector current does not flow, and output voltage becomes negative, high. Result, 0 and 0 inputs, a 1 output. It is possible to build a computer using only NOR-type circuits to perform AND, NAND, OR, NOR, NOT, or any other logic function merely by changing the circuit constants. We come next to the flip-flop. You will recall that a flip-flop is a bistable element operated by pulses applied alternately to the set and reset inputs, producing alternately set and reset output signals. This is perhaps the simplest form of schematic for a flip-flop. 2 PNP transistors and 2 resistors negatively biased. As in our previous cases, negative voltage represents binary 1, and 0 or positive voltage represents binary 0. Note that the bases and collectors are cross-connected, and outputs are taken at the collector connections. The transistors will conduct alternately, the output of each controlling the input of the other. Let's start with this transistor not conducting. Thus, there is no current flow across its output resistor, and the collector voltage, the reset output voltage, remains negative, that is, binary 1. This negative voltage, being cross-connected to the other transistor, causes it to conduct. Current flows, and the collector output voltage, the set output, becomes low, binary 0. Thus, if the reset voltage is 1, it causes the set output to become binary 0. Now, if a 1 pulse, a negative input, is supplied to the base or set input of this transistor, it will conduct. The reset output voltage now becomes low, binary 0. This low voltage, connected to the reset input of this transistor, causes it to cut off. Thus, the set output voltage will be high, binary 1. This condition remains stable because the cross-connection keeps base voltage negative. If a 1 pulse is supplied to the reset input, it causes this transistor to conduct. The set output voltage becomes binary 0. The cross-connected input to the other transistor causes it to cut off. Thus, the reset output voltage becomes binary 1. Again, the circuit remains stable because the cross-connection keeps a negative voltage on the base of the conducting transistor. Outputs will continue to flip-flop as the inputs are alternated. If the pulse that was supplied last to an input is repeated on it, there will be no change in the output because the voltage level on the base is not changed. In this film, you have seen the most common types of logic element circuits, using diodes as well as transistors. These circuits are the basic building blocks of the computer.